All right, so I'm going to have the quizzes graded as soon as I possibly can. Tomorrow we'll go ahead and pass those back. We'll talk about them if you have any questions. Let me finish up and then you can go. Okay, so lots going to be happening in the next couple of weeks. We started talking about this yesterday, so I want to go ahead and refresh your memory. Let me pull this up. All right, so it looks like we're going to be able to get a little bit further through 2.15 today than I had originally thought. So we should be able to finish it up on Monday. That's why I no longer have it right here on Tuesday. So going into next week, we will finish that up. 2.14 assignment is going to be due on Monday. We'll talk about that. We'll have our 2.14 quiz on Tuesday. And then the majority of next week, we're going to be looking at practice exam 1, 40 multiple choice questions. Okay, all different types of topics from throughout the year, all of which are found in that big packet that I copied for you. So definitely, start flipping through that, looking through those old topics. The week after next, I got a couple of days that we're going to be budgeted just for questions on that practice exam 1, and then the majority of the week after next is going to be with the FRQs, the free response questions. So each one is really specific, so you should have an idea of what type of problem you're going to see before going into the exam. Okay, so the exam itself is going to be on Monday the 13th. It is going to be in the East Gym. Okay, so there is something I found out the other day that some folks are probably not going to be too happy with, but let me go ahead and show you this. This is not AP Capstone. So you will be going to certain classes on Monday. Okay, so here's the way it works. If you have a morning exam, okay, well then you won't be going to periods 1 through 5. Those are going to be budgeted for the test you're taking, but you will go to 6, 7, and 8 in the afternoon. If you have an afternoon exam like ours is, it starts at noon on Monday the 13th. Okay, so you will not be going to periods 4 through 8, but you will go to periods 1 through 3. Okay, yeah. Now, if you have one in the morning and one in the afternoon, you should be exempt from all your classes. Guess it depends on how long it is between when you finish one and you have the other. Okay, yeah. Yours is at noon. It's in the afternoon. Mm-hmm. No, I'm not doing anything that day. Basically, if second and third period students have basically if second or third period students have any last minute questions, unfortunately they have a little bit of an advantage because I won't be seeing you that day. Okay. For the other days. I thought they started on the 6th. Or no, yeah, we're on the 13th. You're right. So we are, let me go ahead and take a look here. So leading up to it, I mean, that week of the 6th to the 10th, that's all review. So, I mean, if you happen to miss for another AP exam, I would just, take a look at the website. All the information is going to be posted. I'm going to have a video of it. I would, definitely come in for tutorials, but basically, I mean, we won't be doing any new material that'll be counted as a grade. Why? Why don't you go ahead and talk to your coach about that, because that's something between you and your coach. I shouldn't have to do that. Okay. All right. Any other questions? All right. And one other thing that I'm coming across, and as we go through these next couple of weeks, I'm going to be talking about the policies and what's going to be expected. If you haven't looked at the terms and conditions yet, I would definitely encourage you to do it, because the day of the exam, you're going to have to sign and say that, yes, I understand everything. One thing I came across, you are not allowed to bring any food or drinks with you to the exam. That includes bottled water. Okay, from what I'm reading, it says that when there's a 10-minute break, you can go ahead and get, a drink of water at that point, but you can't have anything with you during the test. So, again, I am not the one coming up with these rules. This is College Board. This is their ball game. I'm just relaying the information. Okay, so giving you a lot more information as we go along, but we got plenty of time for that. So, questions. All right, then let's get started with our final lesson before the AP exam. Let's talk about semi-log plots. Okay, go ahead and pull out those notes there. All right, so a lot of what we do in mathematics is built on what you learned previously. And in this lesson, we are actually going to spiral in several topics that we haven't talked about in a while, one of which is semi-log plots. We introduced those in that particular lesson, and we talked about how to plot points, but now we're going to go ahead and dive a bit deeper. Okay, so what is a semi-log plot? Well, in a semi-log plot, one of the axes is logarithmically scaled. In AP Pre-Cal, we're only going to be scaling the vertical axis. So by the time you move on to calculus, you're going to be scaling both of them, the horizontal and the vertical, but in here, we're only looking at the vertical. So we got a couple of graphs. Now, you probably are not going to remember these, but they are coming out of lesson 2.9. We looked at two graphs displayed above, displaying the population of English Americans in the U.S. from 1620 to 1820, where t equals 0 represented the year 1620. So, for example, if this represents 1620, if it'll let me get my marker here, there's 1620, then this would be 1640, and so on down the road. It looks like 20-year increments. So you may not remember the graphs, but do we kind of remember that scenario? If not, it's in your notes, 2.9. So let's take a look at these. The graph on the left shows the population using a normal scale on the vertical axis. So it's exponential data, it's growing, we would expect to have that smooth curve to it. The graph on the right is a semi-log plot where the vertical axis has been logarithmically scaled. And this is an idea that I kind of floated out there several weeks ago. But if you're working with exponential data and you put it in a semi-log plot like we're talking about here, you're going to be able to see a linear pattern. Okay, the pattern's going to become linear even though the data is exponential. All right, so using this, let's go into example 1. Use the features of the semi-log plot above to justify why an exponential model is appropriate for the population of English Americans in the current U.S. from 1620 to 1820. So I've already got my sentence here, ready to go. The semi-log plot above appears to be blank. And actually, we already answered that question. Appears to be what? What was that? Linear. There we go. Appears to be linear. Now, what would 1660 be? What would be the value of t? 40. 40 years, so the exponential model is appropriate. Now, you remember in previous lessons where we were looking at certain items and we were trying to determine, is this model appropriate or not? Should I use another one? I'm referring to residuals. Okay, so let's talk about residuals for just a second. How do we find a residual? The actual value minus the estimated, the guess. Okay, very good. Now, when it came to a residual plot, was a pattern a good thing or was a pattern a bad thing? Patterns are bad when it comes to residuals. That lets you know that that particular model doesn't work. For a residual plot, if it's just a bunch of random points, you got a good model. Well, another way to decide, for example, if an exponential model is good, if you go ahead and put it in a logarithmically scaled graph like this, a semi-log plot, if the data appears linear, that's another indicator that, yes, an exponential is good to use. Okay. Now, let's take a look at one. Here is a semi-log plot. Now, here's what's really important about this, because it's all about characteristics. And this ties back to, I can't remember the name, lesson number where we were looking specifically at exponential versus logarithmic data, and we were trying to decide which is which. In a semi-log plot, you'll notice the horizontal, the x values, are always going to be evenly spaced. Okay, it's the vertical that are proportional to each other. Okay, we're using base 10. We created it as a logarithm. So that has to be the case here. Now, what are we dealing with if the x's are proportional, but the y values were evenly spaced? It's almost like the direct opposite. What are we talking about here? What's the inverse of a log? That describes an exponential. Okay, so let's take a look at example 2. After Mr. Passwater tells another one of his hilarious math jokes, it begins to spread around the school. The number of people that have heard the joke after t minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for p? Okay, so if you take a look, the thing about this, I really want you to remember, even though the data is appearing in a linear fashion, it's still exponential. You still see the actual value. So for example, this one right here, that would have the coordinate of 0, 2. Okay, remember the base of these, it doesn't start counting at 0, it starts counting at 1. This point right here, this one right here, I'd probably say 3, maybe estimate about 16, maybe even 17. Okay, but this is the exact numbers, the exact data that you would see in the table for the exponential. Okay, and one other thing, because we're going to talk about this in just a minute, but you've got the 3 sections right here. How do we count on the bottom section? Okay, by ones. What about the middle? By tens, and then above by 100s. Now, what if it goes larger than that? After the 100s, we become by thousands. There you go. There you go. Good, good, good. Well, let's go ahead and start taking a look at what we have here. We got minutes, and we got the number of people who've heard the joke. So all of these ordered pairs are going to be of this form here, TP. So the number of people depends on the amount of time that's passed, right? Okay. So what we're going to go ahead and do is use the fact that we have it looking linear, but we are dealing with an exponential model. So let's go ahead and write out a function. Let's start with y equals, okay, b plus mt. Okay. Now, one of the variables I changed, instead of using x, for using t. I'm going to keep it consistent with the problem. But what is that? Okay, slope what? Slope intercept, mx plus b. All right, because it appears that the data is linear. Again, even though we know it's exponential. Here's the thing about this, though. When you're looking at the y values, see, these y values are not evenly spaced. So we can't just use the y value exactly. What we have to do is go ahead and take the log of your y value. And in this case here, your y's are the number of people. That's how we're going to determine how it's placed on the graph. See, we have to take the log of the number of people, the y value, because it's logarithmically scaled here. And in fact, you'll notice, what base did I use? Base 10. Why couldn't I use another base? Okay. Well, it is the common log, but take a look at your vertical axis. What are they using? This is 10 to the 0, 10 to the first, 10 squared, 10 cubed. You're always going to use the same base as what's used in the graph. Is that okay with that? So any questions on how to set this up? Log of p equals b plus mt. Okay. Now, we're going to go ahead and manipulate this in just a second, but let's start looking at our answers. Are there any of these that we could probably get rid of? Okay, Gabriel, what do you think? D? Why D? Well, see, we're starting off with linear because that's what the data looks like. But we actually know it's what? It's exponential. So I'm going to be looking for an exponential model. Now, I know it's exponential because the variable would have to be where? Not in front. It has to be the exponent. The variable would have to be your power. Okay, so with that in mind, I definitely want to keep D. Is there another one I want to keep? I want to keep B. Both of these have the variable as your power. But I want to go ahead and get rid of a because that's just a straight linear function. Okay. I don't know what you're saying, but that's linear. The data just appears linear in the graph. Remember, it's exponential data that we're looking at. Okay. And c is an exponential. It's a what? It's a logarithm. Okay. So we're going to go ahead and get rid of that. So right there, just by knowing that, I've been able to down to two possible choices. I got a 1 and 2 shot. Okay. So now let's go ahead and start to work with this. I've got a logarithmic equation. So why don't I go ahead and convert it to an exponential? Remember, what's my base? Base 10. Okay, so I'm going to say base 10 to what power? Not 2. Remember, we're converting this right here. So I'm going to say 10 to what? B plus mt. Because remember, a logarithm is just a power. And I'm going to set it equal to what? P, the argument. Now, I am going to go ahead and make one change because we're going to go ahead and create the equation, the function. I'm going to go ahead and change P to P of T. And really, it's just using a different notation. Because we said before, P is the Y value, right? But in function notation, P of T still represents the Y value. We're just saying that it depends on the amount of time. So we got 10 to the power of B plus mt equals P of T. Okay, so we know we're dealing with an exponential. Well, you remember one of those lessons where we had an exponential and we rewrote it to look in different forms? Okay, let me give you a what if, for instance. Let's say that I had 5 to the power of x plus 3. This has nothing to do with this problem. This is just an example, kind of like a throwback. Okay, 5 to the x plus 3 power. So could I rewrite it like this? Could I say 5 to the x times 5 cubed? Yeah. See, it's one of those exponential rules. If you're multiplying exponentials with the same base, we add the powers, right? But all of these rules are what? They're reversible. Okay. So I can even go ahead and simplify this. We know 5 cubed is 125 times 5 to the x. And here's what we were trying to stress in the previous lesson. This exponential right here, even though it looks absolutely different from this one right here, they're still exactly the same graphically when it comes to the data. Okay. So with this in mind, let's do the same thing here. So if I have 10 to the b plus mt power, I'm going to say 10 to the b times 10 to the mt power is equal to P of T. Now, you see how my exponential is starting to take shape? Are we leaning towards one answer over the other? What do you think, B or D? Why D? Yeah, how are these two terms right here connected? You're multiplying them just like we have here. What's wrong with B? You're adding those. So right there, I know that 2 times 2 to the t would be a good model. Now, here's the thing. This is only going to work under a couple of circumstances. One, and let me go ahead and highlight the different versions here. Okay. So 10 to the b would have to be 2, and 10 to the nt would have to be 2 to the t. Okay. Now, this is going to work out only under two circumstances. The first power b has to equal the second power m. And as I've already shown, 10 to the b would have to equal 2. So if we go ahead and say that these two statements are absolutely true, well, 10 to the b is 2, so I can replace that with 2. Now, when it says 10 to the m, remember m equals b. So if it's just 10 to the b, there's your second 2 right there. 2 times 2 to the power t. Okay. So that one was a little unusual. So if you're having a little bit of trouble with that, don't worry. There were several people today who were having issues with that. Okay. Anybody have any questions? What time are we out of here? 15. Okay. Yeah. Okay. It's one of those things. Think about, just look at each step. How did I go from this step here to this step to this step? One at a time. Really, it's just skills that we've learned not only in here, but throughout your academic careers. And think about the natural progression of this, how we were able to choose this particular answer. Okay. Now, the rest of this, one part, I wouldn't say it's tricky. It's just you don't want to forget one thing when you're doing it. But looks like we'll go ahead and have to finish this at some other time because we got 2:11. So I'm going to go ahead and stop right there. Like I said, I will get those quizzes graded as soon as I can. And we'll go from there.
So tomorrow during class, finish up stuff.
Yes.